All right, my friends, we'll go ahead and begin. So, last time we learned about this rather heinous mechanism, the Robinson annulation, and this brings together a lot of concepts. And frankly, it's the most difficult mechanism you probably will encounter in 352. So, if you're struggling with it, it's fine. You're supposed to. We talked about how this involves a Michael reaction, which is the reaction of an enolate with an alpha-beta unsaturated carbonyl compound where you attack on the beta carbon. And then there's an intramolecular aldol to give you the more stable six-membered ring product. You get the beta hydroxycarbonyl compound, and then we do the elimination reaction to get this final product. So it's worth reviewing this mechanism. It's worth working your way through it just so you understand what's going on. And as we've been building up our expertise on these reactions, I've told you to pay attention to structural patterns in the products because that will help you recognize what reactions led to those products. For example, we've said that a product of an aldol reaction is either a beta hydroxycarbonyl compound or an alpha beta unsaturated carbonyl compound, depending on whether you do the elimination of the OH group. We've said that the Michael product is a 1,5-dicarbonyl compound, and then that the Claisen product is a beta ketoester. And we're going to introduce one more, and I've told you, you don't necessarily need to think of the Robinson annulation as its own thing because it's really just a Michael reaction followed by an intramolecular aldol. But it can be useful to remember that if you see a six-membered ring with a ketone and a conjugated double bond, we will call that a cyclohexenone. That is the product of a Robinson annulation. And that's a fairly recognizable structural pattern, six-membered ring with a conjugated double bond and carbonyl. If you see that, you could have made that via the Robinson annulation. And if you look at that cyclohexenone, what you see is that the double bond came from the aldol reaction. We made both pi and sigma bonds in the aldol reaction. The sigma bond came from attack of the enolate on the carbonyl. The pi bond came from this elimination step. And then we made this single bond here in red via the Michael reaction. And so what's in purple came from our alpha-beta unsaturated carbonyl compound to begin with, and what's in orange came from what I used as my enolate. So the one thing I sort of wanted to practice before we move on is just recognizing Robinson annulation products and thinking backwards to what the starting materials would have been. So with that in mind and with what you know now, let's draw this strange product. A lot of six-membered rings in this one. This is, I don't know if they call it, what is it called? Aversion therapy. We're trying to break your fear of six-membered rings by just drawing a lot of them. Okay. All right. So there looks like a crazy starting material. And the question is, that looks like a crazy product, and the question is, what were the starting materials? How could I have broken this into simpler starting materials? And so look for this first, look for the cyclohexenone, and that's right here. Do you see that six-membered ring? That's what we could have made via the Robinson annulation. So, okay, if you can recognize the cyclohexenone, you at least know you could have done it via the Robinson annulation, but if you don't know how to break it into parts, then all you'll know is that you're going to get it wrong, and that's not comforting when you're taking a test, right? So let's talk about how you break the Robinson annulation product down. First, identify the carbonyl carbon. Okay. And then label on one side alpha and beta, and maybe even gamma. And then on the other side, let's label alpha and beta. All right. Now, based on what we learned earlier, the double bond, the sigma and the pi bond, came from the intramolecular aldol. So we can do this stepwise, actually, and until you get really good at this, it maybe is a good idea to do it step by step. Okay, so if that is the product of an intramolecular aldol reaction, and it's an alpha beta unsaturated carbonyl compound, so that means there was attack of an enolate and then elimination, or rather attack by an enolate followed by elimination of an OH group. Let's just go backwards to what the product would have been before that last elimination step. So and I'll keep our numbering sort of or identification of atoms scheme going on here. What would the precursor previous to the elimination step have been? I eliminated the OH group, so where was that OH group before I eliminated it? Orange beta, right? Okay, good. All right, so that's an aldol product, right? A beta hydroxycarbonyl compound. In the aldol reaction, what's the bond that we make here? It's this sigma bond between beta and alpha carbons. So let's talk about what this molecule would have looked like. This was the elimination step. Let's talk about what it would have looked like before the enolate attack step. Okay, so let's see. Six-membered ring. So what am I going to have on the orange beta carbon? What would this have been before the enolate attacked? Carbonyl, right? The beta carbon, that's the beta hydroxy here, used to be a carbonyl. In that case, what about the orange alpha carbon? What did that used to be? That would have been an enolate, right, prior to attack. Does that make sense? So this is the aldol reaction attack of the enolate on the carbonyl carbon. Okay, and then presumably we would have made that enolate by deprotonation, and that's kind of boring, so we're not going to draw that separately. We'll just erase the negative charge there. Okay, so that's what it looked like prior to the intramolecular aldol reaction. All right, questions so far about that? You good? Okay. Notice that now that we've thought backwards, those two carbonyls are 1, 2, 3, 4, 5 atoms apart. So that's a 1,5 dicarbonyl, which is a Michael product. So now we're not going to need to number anything over on this side anymore because we've taken care of it, but let's continue to write gamma carbon, and actually let's put carbonyl carbon and alpha carbon here. Remember I told you last time that in a Michael product you can tell it's a Michael product because the carbon that's gamma to one carbonyl is alpha to another. All right, so what's the bond that we could have made via the Michael reaction? This one's kind of hard, so we can zoom out and, whoa, look at the Michael reaction up there in the top corner, if you can see it. But you can't, so okay. Take a minute and learn from that. So now, which one is it? Which bond did we make? Go ahead. Are we going to attack which carbonyl? Sorry. The orange one. To get from here to here, yes, you would make the enolate and attack the carbonyl. But now we're talking about this side of the molecule. We want to break it up into the precursor before the Michael reaction. Yeah? Yep, it's that bond between gamma and beta. So in a 1,5 dicarbonyl, you could have made the bond between gamma and beta via the Michael reaction. So let's take a look at that. The beta carbon in the Michael reaction, this sort of purple side would have been an alpha beta unsaturated carbonyl compound. And then the thing that does the attacking would be here, except what's going to be on the alpha carbon that does the attacking? A negative charge, right? This is another enolate which we would use to attack the beta carbon, right? So, and at this point, the problem is solved. This was our carbonyl compound that did the attacking, and this was our alpha-beta unsaturated carbonyl compound that was attacked. So we have broken the product, which looked pretty complicated, into simpler starting materials. In our 6-membered ring, 4 atoms come from the alpha-beta unsaturated carbonyl compound, and 2 come from the other carbonyl partner, such that now if you look at a cyclohexenone and you number alpha beta gamma on one side and alpha beta on the other, the bonds that you need to make are here and here. Okay? Yes, go ahead. This methyl group? Yeah. Okay. The reason you know it ends up here is because the bond that you're making is between this purple gamma and purple beta, which means everything on this side was part of the thing that did the attacking, and everything on this side was the thing that got attacked. Yeah, so the negative charge is going to be, in the enolate, will have been on this alpha carbon, the orange alpha and the purple gamma, and this is the reason we got the bond here, because this enolate attacked at the beta carbon. Does that see where the methyl group comes from? I mean, in a sense, it's a spectator. It's not really involved in the reaction at all. It's just sort of hanging out there. And frankly, if you can forget for a while you're doing mechanisms or predicting products, you can forget about all the stuff that's not involved in the reaction. Just label everything and then put it on at the end. Yeah?
So then the only reason we know that the starting material on the left that you have, that gets deprotonated on the more substituted carbon, and that's just because like we're doing it in reverse. If we were doing it forward reaction, we wouldn't really know which one of those two get deprotonated.
Sure. So the question is, how do I know, in retrospect, yeah, since we know what the product is, we can find the beginning. How would I know that it would prefer to be deprotonated here versus here? I suppose your kinetic versus thermodynamic enolate would have maybe provided you that intuition. The other thing that you may not have noticed is that this enolate would be conjugated not only with the carbonyl, but also with the benzene ring. This isn't quite as good as a beta dicarbonyl compound, but it's enough to make this enolate more stable than the other one. But you could have made an alternative Robinson annulation product down there. And so, yeah, in a predict the product sense, this is most useful in terms of thinking, given a product and given the starting material, can you do the mechanism? Or given the product, can you think what the starting materials would have been? No, on a test, I would not show you the other possible Robinson annulation product and ask you which one is the one, because that seems particularly nasty. I am evil, but I'm not that evil. Okay, go ahead.
Could the larger starting material be the one with the double bond instead of the small one?
It's a good question. Could the larger starting material been the one with the double bond instead? Right. So I think you're wondering, instead of, right, when we're here, I think you're asking, could we not have maybe broken it up this way, alpha and beta and gamma, and tried to make this bond? Yeah, the thing that prevents that here is the presence of this methyl group. You could not have a double bond here between alpha and beta and still have that methyl group there. Do you see how if I tried to break up the molecule that way, this enolate would need to have attacked something like that? And what's wrong with this? 5 bonds, Texas carbon. Everything's bigger in Texas except for carbons. They still only make 4 bonds, so no Texas carbons. Yeah, so that's the reason you wouldn't know that in this case. Okay. Other questions? So the Smith text, Professor Smith, being a synthetic organic chemist, loves this reaction. This is a reaction that's used, that can be used to make complicated molecules like steroids from simpler precursors. So there's a lot of examples in the text of Robinson annulation products that you're asked to think backward to what the starting material was. So practice that for a while until it's easy, and then you'll be prepared. Okay, anything else we want to say about that? All right, so the next chapter is kind of a fun one to me. I realize that may not mean anything to you. It begins with a question that I've had in the past, which is, there are sometimes reactions that we do that could react with double bonds, but nevertheless don't work with benzene. So as an example, you've learned in 351 that you can do an addition to alkenes reaction where you convert the alkene into an alkyl halide by having the pi bond attack the proton, and then you get a carbocation intermediate that that is attacked by bromine. That sound familiar? Ish? Okay. I mean, you may hate that, which is fine. So actually, I don't like that starting material. Let's try this one so that we don't have to invoke a intermediate primary carbocation. Anyway, the thing is, though, that if you put HBr with benzene, the two just sort of sit there and stare at each other, and you get nothing happening. What this means is that if you have a molecule with both a benzene ring and an alkene like this, the alkene will react, benzene will not. Okay, so there's something special about benzene. We want to talk about what it is and how to recognize it in other molecules as well. So we're going to start by learning how to recognize it, and then we'll finish by talking about why it happens. Benzene is a classic example of a group of molecules that are known as aromatic. That used to refer to the characteristic odor of some of these compounds, but now we use that term not to talk about how they smell, because they all smell different, but rather we use this word aromatic to refer to molecules that are cyclic, have to be cyclic, fully conjugated, and if we wanted to be precise, that's going to mean that we have a contiguous, that's a great word, contiguous, that means connected, adjacent to each other. Probably at some point in elementary school you talked about the contiguous 48 states and then Hawaii and Alaska. Well, that's because the contiguous 48 are connected. So a contiguous array, that means a line. Maybe we should just make this simple, a connected line of p orbitals on each atom of the ring. And it has to be planar. This is sort of, these two are sort of related. I'm not putting them in their own category because if something is fully conjugated, it will be planar. It has to be planar so that the p orbitals line up with each other side by side. And then finally, you have to have the right number of electrons. And we're going to talk about this contiguous array of p orbitals as the pi system. Maybe you've heard of that before. Is that Dienes and Diels-Alder? You talked about pi system, you know, electrons that are, pi electrons are those that are in pi bonds that are conjugated with each other and that are involved in resonance. So in the case of benzene, how many pi electrons do we have? 6, right? 2, 4, 6. The number of electrons, it refers, the number we're talking about here refers to the number of electrons and not the number of atoms in the ring. You have to have the right number of electrons, and that's 2, 6, 10, 14, 18, etc. The pattern here is if we'll let n is an integer, n is just an integer, this defines the series, it doesn't refer to the number of atoms in the ring, then the allowed number of electrons to have this special stability is 4 times n plus 2. So you can see how the numbers I've written here satisfy that equation. And that equation is known as the Huckel rule, named after the chemist who discovered it. When you have these three things, the correct number of electrons in a molecule that's planar, cyclic, fully conjugated, then you have this special stability that is called aromaticity, or the quality or attribute of being aromatic. Meaning you'll have this stability that benzene has that enables it to not react in the same way that molecules with pi bonds react. Okay? So the easiest way to learn this is just to run through a bunch of examples. But before we do that, any questions you want to ask about definitions? Yeah.
So 4n plus 2, what does n represent there?
Yeah, n is just an integer that defines the series of number of electrons that work. N is not the number of atoms in the ring. So you'll see with benzene there are 6 atoms in the ring, but we don't put N in there for benzene. Benzene doesn't have 20 whatever. I can't do arithmetic on the fly. 26. Oh, that's embarrassing. I really, really, really am not good at arithmetic on the fly. I also will get I will confuse my left hand for my right hand almost all of the time. Even though there's a clear difference, I write with my right hand, but anyway. Yeah, so n is not the number of atoms in the ring, it's just an integer that defines which number of electrons give you this special stability. Other questions? And don't worry, it's not like this is magic. This comes from the orbitals of the pi system, and we'll talk about that a little bit later, and I'll tell you where this rule comes from. Anything else? Yeah?
Considering the number of electrons, if there's a lone pair that's attached to, for example, a nitrogen, if that is bonded within the system, do we count those or are they outside the system?
Okay, the question is, what about heteroatoms with lone pairs? Do they count as part of the system? It depends. That's the worst possible answer I can give to that question, so let me illustrate with some examples. It depends on whether the lone pairs are held in one of these p orbitals that's part of the pi system. And here's how you can tell that. So here's a molecule. It's called pyrrole, but we won't worry about it. Let's think about the lone pair on the nitrogen. Is it possible for us to draw a resonance structure where we make that lone pair part of these two conjugated double bonds? Is this a reasonable resonance structure? I mean, it's not great. We don't want a negative charge on a carbon, but it shows you that this nitrogen, which is adjacent to the pi bond, is part of the conjugated system. Now, if the nitrogen is conjugated, look, you've got a pi bond here. So that tells you this nitrogen has to be sp2 hybridized to participate in that pi bond in this resonance structure. And if it's sp2 hybridized here, it must also be sp2 hybridized here, because in resonance there's no such thing as moving atoms. There's no change in geometry. So what I'm telling you is that in this molecule the nitrogen is sp2 hybridized so that the electrons can be in a p orbital where they can line up with the other p orbitals here. If we were looking down at this molecule from the top, then we would see p orbitals on each of these atoms. Those are going to combine together to make 5 new molecular orbitals. But yes, in this case, because that nitrogen, because the lone pair is held in a p orbital on this sp2 hybridized nitrogen, you would count that as part of the electrons, okay? So this molecule checks off cyclic, it checks off planar, it checks off fully conjugated, it checks off 2, 4, 6 electrons. So we have a winner. This is aromatic, okay? How about this related compound in a with a nitrogen in a 6-membered ring where that nitrogen is already involved in a pi bond. What about these lone pairs? Now let's think about, okay, shaking your heads, why not? Why is this lone pair not part of pi system, of the pi system? How can you tell? Okay, you can't include them in a valid resonance structure. Well, can I do this? There are many reasons why that is bogus. Come up with a few. Texas carbon plus never, I mean, in a ring of this size, trying to make a triple bond is really boneheaded because triple bonds require sp hybridization, which linear geometry, so it's not a great idea. So yeah, they're not involved in resonance, and that is the easiest way to recognize that they're not part of the pi system. The second way you can think of it is just to consider, again, the hybridization of the nitrogen, and which atomic orbitals on nitrogen are involved in which of these bonds, right? So nitrogen is surrounded by 3 groups, must be sp2 hybridized. This sigma bond comes from overlap of an sp2 orbital on nitrogen with something on carbon. Same thing with this sigma bond. This pi bond must come from overlap of a p orbital on nitrogen with a corresponding p orbital on carbon. The only thing that's left to house those lone pairs is an sp2 orbital, right? So the lone pairs are held in an sp2 orbital. What the heck difference does that make? And to see this, we have to remind ourselves about geometry. And I'm going to actually draw this ring sort of on its side to give you a sense for what this geometry looks like. Double bond, double bond, double bond. Lone pair is here. If we were to think about the p orbitals that contribute to the pi system, we're going to look sort of like this. We can fill in the wave function sign. I'm just drawing the lowest energy combination in which all of these p orbitals overlap. The only thing that's left for that nitrogen is an sp2 type orbital, on the nitrogen. And notice that, like the other bonds that come from sp2 orbitals on nitrogen, this lone pair is held perpendicular to the pi system. This is why it can't participate in resonance. It can't line up with any of the p orbitals, and if you can't line up parallel with the other p orbitals, you cannot participate in resonance. Orbitals that are 90 degrees away from each other or orthogonal do not interact. Simple explanation for that is it's sort of like, okay, help me out here. Which one is it that's 0 for vectors? Is it the cross product or the dot product? Vectors that are 90 degrees apart, I forget. Is it cross or dot? Yeah, so it's kind of a dot product issue. That may not make it easier for any of you. It certainly hasn't made it any easier for me. But orbitals that are 90 degrees apart do not interact with each other, cannot participate in resonance. So the lone pairs here are on their own, and they are not part of the pi system, right? So is this molecule aromatic? It is cyclic, planar, fully conjugated, and has 2, 4, 6 electrons, 6 pi electrons. These don't count, all right? So yes, we have another winner. This is, in fact, aromatic. Okay. Yes?
Can you give us an example of a cyclic structure that's not planar that would be aromatic?
Can I give you an example of a cyclic structure that's not planar, that's not aromatic? Yes. I can give you lots. So let's... That is not aromatic. because it is cyclic, but it's not planar. You've got sp3 hybridized atoms there. So the geometry would not be planar, at least not here. And it's also not fully conjugated. Okay. So, and there are others we could think about. But I want to return to this issue of like what to do with heteroatoms. Let's imagine you have this molecule. Lone pairs everywhere. All right, which ones count as part of the pi system and which don't? Let's deal with the nitrogen first because this nitrogen is most similar to the one we've already encountered. Are these lone pairs part of the pi system? No, they are not. You can tell that if you want a quick way. The nitrogen is already involved in a pi bond, so your p orbital is already used. The lone pair on that nitrogen must be in an sp2 orbital and is not involved in the pi system. So, okay, let's talk about oxygen. Which one of, which one is the wrong question? Are all of these involved in resonance? One or none? Maximum of one. So justify that for me. Why is that the right answer? I can't hear your whispering. Go ahead.
Both of them were included, then you would have 8 electrons and it wouldn't be aromatic.
Okay, if both of them were included, you would have 8 electrons and it wouldn't be aromatic. That's true, but we're going to see molecules that are not what's called anti-aromatic because they have 8 electrons. So why does only one participate? Yeah.
Because you can only double bonds, draw a resonance structure where you move the top double bond over, the electrons over, and then you can draw a double bond. Yeah. That doesn't work the other way.
Okay, so at most, I can make one of those lone. What did I do wrong? Nope, there we go. At most, you can make one of those lone pairs involved in resonance, right? And when you do, you see that the other, if this oxygen truly is sp2 hybridized, the p orbital is the one that holds one lone pair, and the other must be held in an sp2 orbital, right? There's a maximum of one lone pair on a heteroatom that can participate in resonance and aromaticity because only one of them can be in the p orbital, right? So you're going to have to get good at recognizing which electrons can be part of the pi system. The ones that count, I will label here. You got 2, 4, and 6. So this is indeed aromatic as well. All right. So those are some sort of tough examples. The book is going to take you through a ton of them. If you're struggling with it, make sure when you get a problem wrong, you figure out which of those things your molecule violates, and pay attention especially to molecules like this that are aromatic, but you say they're not because you counted the electrons wrong. That's going to help save you some pain in the future. I want to talk about molecules that are cyclic and but have the wrong number of electrons. Okay, let's see. Do this. Yeah. Well, before I do that, another boring example of a molecule that's not aromatic is that one. It's fully conjugated. You have p orbitals on adjacent atoms, but it's not cyclic, and so there's no aromaticity. And really, we'll sort of explain why. It might be perplexing as to why benzene with the same number of pi bonds and also resonance is still more stable than this one, and it has to do with a molecular orbital theory argument that we'll get to a little bit later. Now, what about compounds that have the wrong number of pi electrons? This is cyclobutadiene. It is cyclic. It is fully conjugated. But how many pi electrons does it have? Just 4. So in terms of aromaticity, we put the big ekis on that one. And so this is, and not only is this not aromatic, because it has the wrong number of electrons, it's going to be called anti-aromatic. Molecules where n is an integer, 0, 1, 2, 3, and so on, molecules with 4n pi electrons are anti-aromatic. Just as aromatic molecules experience special stability, anti-aromatic molecules experience special instability, for reasons we will talk about when we get to the MO picture of aromaticity. But for now, just know that if you have the wrong number of pi electrons, you are anti-aromatic. So there's sort of 3 categories a molecule can fall into: aromatic, special stability; anti-aromatic, special instability; and just plain old boring not aromatic, which if a molecule is simply not aromatic because it's not cyclic or not fully conjugated, then we don't have to worry about whether it has the right number of pi electrons. Okay. Another example of an anti-aromatic compound is this lovely stop sign molecule, cyclooctatetraene. This would be cyclic, fully conjugated, but it would have 8 electrons, 8 pi electrons, and so it would be anti-aromatic. Cyclobutadiene is so reactive that you can't observe it unless you freeze it in a matrix of solid argon at 4 Kelvin, and then you can observe it. Or you can make a beautiful molecular box to contain it, and then it can exist at room temperature indefinitely. I'll bring in a model of the box that can hold cyclobutadiene next time. But this is kind of organic chemistry's nerd compound. Like it was always a task to see if you could observe it and measure its properties. One of the things that is observed is that molecules that are anti-aromatic will often distort their geometry so as to be not aromatic. For example, cyclobutadiene will actually lengthen its sigma bonds and then twist the pi bonds a little bit out of conjugation to make it more like a molecule that has 2 double bonds instead of a molecule that's full-on anti-aromatic. And cyclooctatetraene, you can actually, this is neither here nor there, but it's kind of funny. Cyclooctatetraene is often called a cod because of that, not because it looks like a fish. I don't know where the D comes from. Huh. Maybe not. Oh boy. In any case, this will distort its geometry so that it's just not planar and not fully conjugated. So it adopts this sort of strange boat-like structure, which I'm struggling to draw, with the double bonds sort of out of conjugation with each other. And that, when it distorts itself, it breaks apart the anti-aromaticity, and so you can observe cyclooctatetraene. So this is an example of molecules that are neither aromatic nor anti-aromatic because they're not planar. However, if I were asking you, if I were asking you about cyclooctatetraene, you would just call it antiaromatic. Okay, just know that antiaromatic molecules will often distort their geometry, so they don't have to be antiaromatic. All right. Now you can use aromaticity to explain some interesting observations. So let's draw the following two molecules. People have told me that my 7-membered rings with 3 double bonds in them look like sad robots. And he does, kind of, right? Looks very distressed. I don't know what's wrong. One of these protons is more acidic than the other. So let's consider which one that might be. To compare acidity, we draw the conjugate base. So let's draw the conjugate base of both of these molecules, in which a proton would have been removed, and then we're left with a negative charge on the corresponding carbon. Sorry, she's laughing at the sad robot. Okay, take a look at these and tell me which one is more stable, using what you know now about aromaticity. Go ahead, the one on top. Why? It's aromatic. That conjugate base is aromatic. How about this one? This would be anti-aromatic. How can you tell? 6 electrons here in the pi system, 8 here in the pi system. Okay, so you can use aromaticity to explain why this proton is much more acidic than this one. Interestingly, this is an unusual conclusion, right? Because if you didn't know about anti-aromaticity, you'd say, well, I don't know why one's less stable than another, one's more acidic than another. They're both adjacent to pi bonds. The negative charge in both can be delocalized. What's the big deal, right? So you need to know about aromaticity to predict this result. Go ahead.
I don't super get like why aromaticity makes it more stable, because in my mind it's just like, yeah, the more pi bonds involved in resonance, the more spread off the negative charges. Like, is it the shape or like what?
What is it about aromaticity that makes things more stable? Yeah. So the short answer is related to something I think you learned about in the chapter on conjugation. I don't know if you recall learning that conjugation involves multiple p orbitals lining up on adjacent atoms. This is the lowest energy pi molecular orbital. We're just looking at the top lobes of these p orbitals, and you see you have adjacent p orbitals lined up next to each other. And each of these adjacent things can be considered a bonding type interaction. So in this molecule, you have 5 times where p orbitals are adjacent to each other with the same wave function sign. Now, look at the difference when you turn that conjugated molecule into a cyclic molecule. Now, the cyclicness of the molecule gives you 1 extra element of overlap. Now, instead of 5 times where things are adjacent to each other with the same wave function sign, now you've got 6. So that's a bonus bonding interaction, and this molecular orbital is therefore lower in energy than this one. And that's the special stability you get from aromaticity. Yeah? Do I know the pKa difference? That would be good for me to have written down in my notes, but I did not. So I'll look it up and tell you next time. If you have questions, come on up, and I'll answer them. And I will see you guys on Friday.